Okay, YouTube, in my last video we started to take a look at systems of linear inequalities. In this video we're going to continue our kind of exploration of that, but use a little bit more vocabulary as well as do an application problem in which we could apply this type of technique for looking for solutions, okay? So it says we're selling adult tickets $5 a piece and youth tickets for $3 a piece for a school play. And we want to sell at least $600 worth of tickets, okay? So the two things we want to do here, first of all, write and graph a system of linear inequalities that describes what we were just told, that information. But also, we want to ask this later on, well, if we did sell 80 adult tickets and 100 youth tickets, did we reach our sales goal? Which is something, by the way, we could calculate right now. I mean, we don't have to draw a graph to figure this out. I want you to think, how could I use the fact that I sold 80 adult tickets and 100 youth tickets to reach our goal or not, at least 600 bucks, okay? So when you look at a system of linear inequalities, there's kind of one thing that gives it away is you start to use language like at least and at most, okay? So when you talk about at least, let's go ahead and write down a few things that we want to keep in mind here. When you hear at least, it means that we're talking about greater than or equal to. If something is at least as much as something else, it's at least as big as it or bigger than it. And when we hear at most, okay? So we hear at most, I want to be thinking less than or equal to, okay? If I want less than or greater than, we just flat out say less than and greater than, okay? So this is how you'll see these things probably spoken in a sentence. So we say less than, greater than. Okay, so those things down. When you read through a problem like this, you always want to underline units, okay? So this is an important thing to do. It's a good, not even a skill, but we say underline important units. So we've got those underlined for a reason. Because we typically formulate equations with units in mind, okay? So we say underline important values. For the sake of these here, we need to come up with a few constraints that describe this situation. So first things first, when we talk about x and y, we have to define these, okay? So define variables. So underline important values, define variables. The way you typically define your variables is it's the stuff in the problem that you're kind of considering, or the things that are changing, for instance. So when I read through this and it says we're selling adult tickets and youth tickets, I'm thinking, well, those are the things that I'm kind of paying attention to here. So we're going to let x equal the number of adult tickets, and then we're going to let y equal the number of, we'll go youth tickets here, okay? The important thing is that you write number of. We have to make this some sort of quantity that we can count. But in terms of the inequalities that I can think of, the first one that strikes me here is I'm not going to be selling negative tickets. So one thing we typically always write on any type of application problem, when we're talking about common things, which are like real life tangible things, are these two constraints. They are common constraints. They're not always present, but they are typically there when you're talking about application problems, because what this means is that you're in the first quadrant. Your values of something that you're talking about are up in the first quadrant. You have positive x's and positive y's, or at least non-negative. The second thing, suppose we can mention here, is this. You hear me using this word constraint. When you graph a system of inequalities, you're looking for a solution region. And so that region is well defined by certain inequalities that shade one way or another. So we look for those outlining inequalities, and we refer to those outlining things as constraints. So when you hear constraints, it just means your inequalities, okay? So common constraints, make sure you include those. The third constraint is going to come about from these dollars. And notice that I have dollars and dollars and a total amount of dollars. And in this relationship, if we read through this, we say, oh, well, we're selling $5 adult tickets and $3 youth tickets. And I asked you to consider this, would you make enough money if you sold 80 adult and 100 youth tickets? I mean, would you make your goal of at least $600? We could figure this out. You just take $80 times $5 a ticket, and then you add that on to $100 times $300 a ticket here. You probably do it in your head and got it figured out right now that it works. But how to write this constraint is the same way. We're going to say, well, we sell 80 adult tickets, 100 youth tickets. Those are the things I'm talking about, and we'll match up our dollars now. So we say $5 times the number of these plus $3 times the number of those, and we want at least $600. So when you hear words like at least, hey, we're talking about an inequality. So let's go ahead and graph these three constraints. Okay, so once you've got your constraints written, let's see, write the constraints. Write the constraints, I suppose, would be the third thing we did there. We're going to graph the constraints. Okay, and I'm going to make some suggestions here when we do this, of course. But the first thing I recommend is this. Go ahead and graph the lines associated with these. We'll shade last. So let me switch out here. Let's go gold. So we say here's my x equals 0. We need to drop in our y equals 0 line. Sorry about the right edge there. These are both solid, okay? Also this, we say, well, I need to find the intercepts on this guy. So to find the intercepts, it's in standard form. We'll plug in 0 for x and 0 for y to find our y and x intercepts respectively. But plugging in 0 for x, you'll notice you get 3y equals 600. So 600 divided by 3, I get 200 exactly. And then if you plug in 0 for y, that is, you'd have 5x equals 600. And 600 divided by 5, I think, is 120. So we have 120. The reason why you want to find your intercepts first before you graph is because you can tell what kind of scale you need to go by. Like, am I going by 1s, 2s, 10s, 25s? You know, you figure this out. So we say graph constraints. One side note we want to write here is this: find intercepts first. You want to find those first. Okay? And then say a subclause here also, choose appropriate scale. You know, that's what we wanted to do here. Appropriate scale. And what I mean by is like what you're going by on these axes. Okay, so now keep in mind that this is a number of adult tickets down here. We don't always label the graph. I mean, you should, but we say number of adult. Number of, youth is our axis over here. But it looks like in terms of our intercepts, we need to go out at least 200 on our y-axis, go up at least 200, and at least 120 out on our x. So I think if we went by tens, let's count here. We say 1, 2, 3, 4, 5. Each of these blocks is 5, so 5, 10, 15, 20. We can get a y-intercept of 0, 20 up here. It'll fit. And then 120 would be group of 5, and then 2 more. This is this x-intercept, 120, whoops, comma, 0. And then so we can connect this with a solid line, pardon the rough line here, and label this. So we say this is the line 5x plus 3y equals 600 when you label the line. But let's test the point 0, 0 on this. I don't need to test points on these top two constraints. I can see that they really say that you're going to hang out in the first quadrant. But when you look at this third constraint, you test 0, 0, you can see clearly it fails. You would get 0 times 5 plus 0 times 3, which is 0, and you get this statement 0 is greater than or equal to 600, which is false. So this is not true, so we would shade outward. So this is the interesting thing about it. I'm going to extend my reading a little bit here, but we say, so where's the set of acceptable solutions? Remember, this constraint here went up and down forever, so it shades in. So when we shade this in, let's switch this color over to like a teal. Yeah, that works. I'm going to shade the outline of my region. This is what I always suggest people do. But I can see that all of the arrows are shading together in this area right here, which means, I could shade all of this. We say anything in this region is going to satisfy this. So going back to the original question, that was part A. We say part B, if we sold 80 adult tickets and 100 youth tickets, keep this in mind. We say adult tickets are our x value, so we're saying 80 is our x. And 100 youth tickets, that's our y value. So 80 comma 100, really what I want to be going and looking for is 80 comma 100 in this region. And so I say, well, go over 8. Over 8 is here. And we say up 100, that'd be up 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's right here. And so all I want to say is yes, clearly this is in the solution region. So to answer our question with the graph, absolutely we could see that would help us reach our sales goal. But that's how you set up a system of constraints. Once you graph those, step 5, and go ahead and add this in now, but find all vertices. Find all vertices, okay? And right now, it's cool to just put a box around them. And I see that I have 2 here, and that this would be some unbounded, feasible region, okay? Unbounded, feasible region. Groovy.